You know that momentary, satisfying little tap you make on a banner ad? Well, that single interaction sets off a hidden, continent-spanning chain reaction in literally a matter of milliseconds. That one tap triggers financial transactions, it updates complex analytical dashboards, and it completely reshapes campaign strategies for advertisers who are spending millions of dollars. In this explainer, we're looking at the invisible infrastructure that acts as the currency pipeline for a massive, multi-billion-dollar industry. But think about it. How do platforms like Google, Meta, and Amazon actually ensure that every single tap is counted correctly when the stakes are just this high?
To really wrap your head around the problem, you first have to understand the sheer mind-boggling scale of it all. We're talking about peak throughputs that frequently blast right past 100,000 clicks per second. To put that into perspective, that is more events happening in a single second than a massive sports stadium experiences over an entire weekend. These systems are ingesting raw events at an extreme scale from mobile phones, web browsers, and smart TVs all across the globe. And they have to do it flawlessly. If this infrastructure breaks down, advertisers overpay, publishers lose their revenue, and basically trust in the whole system collapses entirely.
So how exactly does a tech giant process billions of ad clicks in real time? Designing an ad click aggregator is honestly one of the absolute highest-stakes system design problems in software engineering today. It sits right at this crazy intersection of real-time analytics and rigorous financial auditability. Today, we're going to unpack the engineering magic that makes all of this possible, looking at how they prevent lost data and stop duplicate billing dead in its tracks. Okay, let's dive right into the architecture.
First up, the dual pipeline architecture.
So, at internet scale, no single data pipeline can simultaneously optimize for both absolute correctness and real-time freshness. It's just not possible. Because of this, production systems require a dual pipeline architecture. This flow brilliantly illustrates the physical path of our real-time streaming pipeline. When a user taps an ad, the event hits an edge API. It gets buffered right into a distributed Kafka queue, then it's processed and aggregated by Apache Flink, and finally, it lands in an OLAP database where it pops up on an advertiser's dashboard. But remember, this streaming path, it's really only half the story.
Here is exactly why we need two paths. The streaming path, the one we just walked through, is optimized for pure speed. It provides fast estimates so advertisers can see pacing metrics on their dashboards within seconds. But, as we all know, networks are super messy. Events get delayed, they get duplicated, so running parallel to this is the batch path. This batch path takes raw events and writes them directly to highly durable storage, like Amazon S3. Then, hours later, it slowly and meticulously reconciles every single event. A great way to think about it is like this. The real-time numbers are your fast estimates, but the batch truth, that's what generates the final invoice.
Moving on to ingestion and event streaming.
Now, this layer is incredibly latency sensitive because it sits right on the critical path of the user's web experience. When a click actually happens, it hits an edge ingestion service, which is a server physically located as close to the user as possible, just to keep that latency perfectly under 50 milliseconds. But obviously, it can't just accept any random data. It performs really strict validations. It verifies the schema, it stamps the geographic region, and most importantly, it checks an HMAC signed impression token. This cryptographic signature is absolutely crucial because it ensures the click is legitimate and completely prevents fraudulent replay attacks, where malicious actors might try to artificially inflate a competitor's ad costs.
Right after it's validated, the Edge service immediately drops the event into Apache Kafka. You can think of Kafka as the system's massive, durable shock absorber. Traffic on the internet comes in unpredictable, sometimes gigantic waves. Kafka decouples this chaotic, wild ingestion rate from our steady downstream processing. It safely stores these click events across replicated partitions. So, what that means is, even if a server completely crashes and burns, the data is safely persisted to disk and absolutely nothing is lost.
Next, let's look at real-time stream processing.
Welcome to the absolute brain of the operation. To transform millions of raw, messy events into clean, actionable business metrics, we have to achieve what engineers call exactly one semantics. And this right here is the holy grail for ad systems. It guarantees that an event is delivered and processed precisely once. No more, no less. Imagine a user's phone drops its connection and retries sending a single click 3 times. Well, the ingestion layer might actually accept all 3, but our stream processor absolutely must filter out those duplicates using a 2-phase commit protocol. The whole point here is making sure advertisers are never, ever double-charged just because of a temporary network hiccup.
But wait, what about delays? Let's say a user clicks an ad right before their train goes into a tunnel, and the event doesn't even reach our servers until 2 minutes later. Stream processing frameworks like Apache Flink handle this using something called watermarks. Watermarks track the progress of the actual event time, meaning when the click physically happened on the phone rather than when the server processed it. This awesome mechanism allows the system to organize out-of-order clicks into perfect little 1-minute time buckets, gracefully waiting a specific defined amount of time for any late-arriving data before finally closing the window.
So just to summarize the heavy lifting that's constantly happening inside Flink, it's reading continuously from Kafka, it's deduplicating those events using unique event IDs within a bounded time window, it's updating stateful running aggregates like keeping track of the total clicks for campaign A, and then it's continuously upserting those fresh, updated numbers right into our analytics database. And the crazy part? It is doing this for thousands and thousands of campaigns simultaneously.
Section 4. High-speed analytics storage.
Okay, so now that we've accurately counted all the clicks, advertisers naturally want to view them on those slick, interactive dashboards, slicing and dicing the data by region, device, and campaign. To serve sub-second queries over literally billions of rows, a traditional database would just completely choke. Instead, we use specialized technology, online analytical processing, or OLAP databases. These use columnar storage, which compresses similar data together so it can scan billions of rows in milliseconds. As you can see, engineering teams usually choose between absolute titans here. You've got ClickHouse for raw vectorized speed. Apache Druid is great for seamless Kafka ingestion. Or there's Apache Pinot, which leverages star tree indexing to handle massive concurrency. Perfect for when thousands of advertisers log into their dashboards at the exact same time.
Finally, let's talk about engineering for extreme scale.
So the internet is rarely well behaved, right? And that chaos leads to some pretty major distributed system nightmares. The most notorious issue we face is called the hot shard problem. Usually, we partition our Kafka queues by campaign ID, so all the clicks for one specific ad go to the exact same processing task. But imagine a highly anticipated Super Bowl ad drops. Suddenly, that single campaign accounts for maybe 30% of all global click events. That specific campaign's traffic completely melts a single Kafka partition and overwhelms one Flink task, causing massive latency spikes. Meanwhile, the rest of your servers are just sitting there completely idle.
To fix this nightmare, engineers use a really brilliant trick called key salting. When the system detects a viral campaign starting to spike, it takes that hot campaign ID and appends a random suffix, or salt, to it, sort of like appending a random number from 1 to 10. This expands that single logical key into multiple physical keys, which perfectly distributes that crushing load across many different partitions. The stream processor then computes partial aggregates for each of those salted keys and safely merges them all back together right before writing to the database. It is an incredibly elegant solution to a massive system-breaking bottleneck.
From the exact moment a finger taps a screen, routing through Edge APIs, Kafka queues, Flink windows, and finally hitting those OLAP databases, every single piece of this beautifully complex architecture serves one unified goal: unshakable financial trust. Because at internet scale, trust really is currency. So the next time you casually tap a banner ad on your phone, just remember, you aren't just opening a web page. You are literally stress testing one of the most sophisticated, distributed financial engines ever built. And the real question isn't just how they processed your click today. It's what crazy architecture they're going to have to invent to process the next trillion.